test, test. In my example, I am talking about an observer at 1/6 of the explosion center. So if I imagine sort of a space-time diagram with time, I'm going to draw the time axis going this way, and the x-axis going this way, with x equals 0 here. This line is described by x equals ct, and this line is drawn by x equals negative ct. So an observer at 1/6 of the explosion center would be traveling. Okay, the explosion, if there was an explosion here, then we would have this line be described by x equals negative ct over 6, and this line be described as x equals positive ct over 6. And we're going to put an observer right here. There's our observer. Says the observer only deals with his backward light cone, of course. So we'd be looking at a light cone coming down this way and this way, and observes objects that appear to have redshift such that the object at 1/6 on the other side is observed. So he's going to be looking at an object right here. The example is axial symmetric to a flat surface of cross-section. The example is axial symmetric, so a flat surface cross-section through the whole system is enough. All right, so let's go ahead and put in the central observer. Which would be at x equals 0. So here's, I think this might be something I disagree with. The example is axial symmetric. Not from his point of view, it's not. Well, this is the axis in his point of view. Where is the line of simultaneity, if that's his axis? They scissor, so the line of simultaneity is going to be kind of like right along here. So this is, should I do that in a different color? Yeah, so with that event, that line, this is close to the line of simultaneity. And what that line of simultaneity does, it preserves the speed of light. So what we will see is that this part of it is axial symmetric. We'll have the line from here to here is the same as the line from here to here. So these two, this is the axial symmetry, or along from, so the example is axial symmetric. So a flat surface cross-section through the whole system is enough. So this is going to be our cross-section. This is going to be the flat surface cross-section through the whole system. So in this diagram, it's orthogonally, what's it called? It's orthogonally perpendicular. It's hyperbolically orthogonal, which means whereas normal orthogonality would be x equals, if we had y equals mx, for the perpendicular line you'd have y equals negative 1 over mx. This one has hyperbolic orthogonality with this line here. So it's kind of the opposite. This one has x equals ct over 6. this line should have x equals 1 over, oh, okay, negative ct over 6. This line should have just the reciprocal of that, negative 6 over ct as its, no, sorry, negative 6 over c. It's not the reciprocal of the whole thing, just the reciprocal of the constant. So here it's m and negative 1 over m. Here it is slope negative c over 6 and slope negative 6 over c. So that's your Euclidean orthogonality, and this is hyperbolic orthogonality. Okay, now the difficult part of this, the part that I don't think I'm going to be able to do without software help, is turning this into a three-dimensional figure and figuring out how to map these points so that this this inner cone should be a cone advancing at 1/6 the speed of light, and we're going to figure out, well, it depends which one is of interest here, because he kind of said something about the backwards light cone, and he also says a flat surface cross section. So actually both of these, the backwards light cone can be mapped to a flat surface cross section, but also the plane of simultaneity. The plane of simultaneity can be easily mapped to a flat surface cross section, but we can also do a we could also worry about the backwards light cone, which is a different set of events. But one of these represents kind of a well, let's just call them observable and unobservable. What's going to be observed is every spot where this light cone kind of meets with that light cone. So you're going to have this region. I should maybe draw that in a different color, maybe. So you'll have kind of this region where it connects with that red, where that blue cone intersects with that red cone. And I don't think I did any justice to that at all in this diagram, because actually no, it should extend all the way up to here, right? So where that blue cone, I'm gonna hit Control Z a few times and imagine, let me try to draw that again. I was drawing in green. So that blue cone intersects the red cone there, and it intersects the red cone there, and it creates this whole region here. This is the intersect, basically in the 3D diagram, those events that are observed at this moment are mapped into that region there. And that's going to be a big oval shape. But if we consider where those events are, where the blue cone intersects the plane of simultaneity, it's going to be a cone somewhere around here. But those events won't be what the observer here actually observes. That would just be what he would calculate to be the simultaneous position of all of those particles. But he won't be able to actually determine that for sure until sometime later, when all of the light from all of those events actually reaches them. Wait. No, actually by this time the light from those events already has reached them, but he's just now receiving this last event. yeah, he's getting this event at that point. And so he would be, at that point, he would have gotten his final data point about what the what that scattering was doing during that time. But he's including in that set something that happened at his own position.